Millions of developers, billions of lines of code. GitHub and VS Code are the primary arteries of the global software ecosystem. Everyone from nascent startup founders to senior engineers at Microsoft and Meta rely on these platforms to build our digital infrastructure every single day. In this environment, speed is the ultimate metric. The pressure to innovate drives a relentless momentum, fostering a developer culture heavily focused on moving fast, building quickly, and deploying software updates to the world in a matter of seconds. To maintain that blistering pace, programmers rely on third-party extensions. These are add-ons that customize their coding environments and automate tedious tasks. Developers download and install these tools thousands of times a day, operating on a deep, implicit trust in the marketplace. But this diagram shows what happens under the hood when installing a single, seemingly simple tool. It instantly expands into a sprawling web of underlying dependencies. Each piece of hidden code comes from different sources and rarely undergoes an independent security audit. That combination, a culture of implicit trust mixed with massive, hidden software complexity, created a vast and invisible attack surface. It left the front door wide open for a catastrophic infiltration. In late April 2026, security teams at GitHub noticed highly unusual patterns in their server traffic. Internal data was actively leaving their infrastructure, routing toward unknown external IP addresses. Around the same time, individual developers across the open-source community started experiencing odd glitches. Project compilations were failing randomly, and unexplainable temporary files were quietly materializing on their local hard drives. Those scattered glitches were the early symptoms of an enormous supply chain breach. Over 80 of the most widely used programming extensions for languages like Python and tools like Docker had been infected, exposing an estimated 5.3 million developers worldwide to malicious code. The precise tools the industry trusted to build the future of technology were actively dismantling internal networks from the inside out. To understand how a system this highly monitored failed, we have to trace the attack to its origin. The perpetrators didn't start by hacking code. They started by manipulating human psychology. Using highly convincing fake domains that mirrored internal Microsoft login pages, the attackers launched a targeted phishing campaign. They tricked senior GitHub engineers into handing over their credentials, completely bypassing multi-factor authentication in the process. With those elevated credentials secured, the attackers moved laterally through GitHub's internal systems. They searched until they discovered an unpatched zero-day vulnerability in the cloud services used to test and deploy software updates. The attackers bypassed manual code reviews by leaving the raw source code untouched. As this diagram illustrates, the malicious module bypassed human inspection, entering only during the final packaging phase. Right before publication, the malware was embedded as a hidden dependency, packed alongside the clean code, hidden entirely inside the finished product. By infecting the software at the absolute last step before distribution, the attackers bypassed the most sophisticated monitoring systems in the industry, creating a perfectly invisible digital Trojan horse. For the end user, everything looked entirely normal. A developer would download a popular coding tool, expecting a simple workspace upgrade, completely unaware of the payload attached to it. The moment that download completes, a hidden pre-install script instantly triggers in the background of the user's machine. This script sends a quiet ping back to the attacker's command servers. It reports the victim's operating system, processor type, and active antivirus software, waiting for specific instructions on how to proceed. Based on that ping, the main malware, known as CodeSiphon, deploys. This schematic shows CodeSiphon operating as a fileless threat. It avoids writing to the hard drive, embedding directly into the RAM. Operating from memory, it extracts API keys, steals source code, and injects cryptojackers to drain computing resources. Because it lived in volatile memory rather than on a physical disk, the malware robbed the world's top tech companies blind, while leaving almost no footprint for traditional antivirus software to detect. By mid-May, the full scope of the damage became clear. In roughly 14 days, the attack resulted in $3.5 billion in estimated financial losses, with over 180 terabytes of proprietary data stolen. GitHub and Microsoft initiated an immediate global lockdown. They purged dozens of top-tier extensions from their marketplaces and automatically revoked millions of potentially compromised API tokens and SSH keys. To help individual developers clean their local systems, Microsoft deployed the CodeSiphon Scanner, a free emergency tool specifically designed to hunt down and eradicate the memory-based malware across millions of machines. While the immediate infection was contained, the breach exposed a systemic vulnerability in the supply chain. At the time of the attack, digital signatures were optional, meaning millions of developers were effectively running unverified code by default, with no way to prove its integrity. The crisis forced structural changes. First, digital signing is mandatory, blocking extensions from publication without a verified cryptographic signature. Second, a required software bill of materials exposes every underlying component and hidden dependency, ensuring users know exactly what's running. Finally, tech giants integrated AI-driven behavior analysis into their infrastructure. These systems constantly scan for the kinds of suspicious memory and network activities that human code reviews naturally miss. Working together, these overlapping layers of defense permanently hardened the entire global development ecosystem against any future supply chain manipulation. The CodeSiphon catastrophe forced a permanent pivot in development priorities. The industry still values rapid innovation, but today, speed is secondary to a verified and secure supply chain.